Welcome to the core definition of Rust. While other languages rely on garbage collectors, Rust uses third way, and that's ownership. The simple idea makes Rust memory safe with zero runtime cost. It is governed by three simple rules. In this video, we'll start with three foundational rules, dive into scope, the stack, heap, and concepts like moving, cloning, and dropping. Finally, we'll see how ownership acts across function boundaries, setting stage for references. Everything revolves around the three Ironclad rules. 1. Each value in Rust has single owner. 2. There can only be one owner at a time. And 3. When the owner goes out of scope, the value is dropped. Memorize these, everything else follow from them. Let's start with scope, the range where a value is valid. When you declare a variable, it comes into scope and becomes valid. It remains valid until execution hits the closing braces. At that exact moment, the variable goes out of scope and is dropped. To manage memory, Rust uses the stack and the heap. The stack is fast, fixed size, and pushing and popping data like plates. The heap is slower. This is where you request space for dynamic data. Ownership exists primarily to manage this heap data. Consider the string type. A hard-coded string literal is fast but completely immutable. The dynamic string type, however, is heap allocated. It can be mutated and grown at runtime, making it exactly the kind of complex data that ownership is designed to safely manage. Heap memory has a strict contract, request space from the allocated and later return it. Other languages uses heavy garbage collectors or force you to free memory manually, causing bugs. Part 2 of this contract is where Rust's brilliant answer comes in. Rust answer is automatic. Memory is returned the exact moment the owner goes out of scope, at the closing braces. Rust automatically calls a special function named drop. No manual free, no garbage collector, just perfect cleanup at compile time. But what about simple, stack-only values in integers? If we assign x to y, Rust makes a completely cheap independent copy right on the stack. There is no move here, both variables stay valid and usable, contrasting to how string behave. To understand that contrast, look at the string's anatomy. It has two parts, a stack record containing a pointer, length and capacity. On the heap, the actual text bytes. The stack simply points to the heap. Remember this shape, it's key to everything. So what happens if you assign string 1 to string 2? Rust copies the small stack record, pointer and all into a new variable, but crucially it does not copy the heap bytes. Now we have two distinct stack records pointing to the exact same heap buffer. This creates a massive danger. If both variable tries to free that shared buffer, it would trigger a fatal double free corruption. Rust prevents this by instantly invalidating the first variable. This combination of shallow copy and invalidation is called move. The move guarantees safety. If you try to actually use that first variable after it's been moved, the compiler stops you. It highlights the exact line and throws a border of moved value error. This memory bug is caught entirely at compile time, never shipping to the users. Why did Rust move it instead of just copying the heap? Because cloning heap data takes heavy CPU cycles. Rust has strict rule, it will never silently make a deep copy. Any automatic copy it makes it guaranteed to be extremely cheap and fast. Ownership also perfectly handles reassignment. If a variable owns the word hello and you reassign it to ahoy, nothing points to hello anymore because ownership is lost. Rust automatically drops the old memory instantly. You never have to wait around for cleanup. But what if you really do want two independent strings? You must explicitly opt in by calling .clone. This tells Rust to duplicate the heap data, so both variables own their own buffers and stay valid. The clone method is a visual signal for expensive operations. So why did integers copy automatically earlier? Because simple fixed size stack types implement a special trait called copy. But a type cannot be both copy and drop. If it needs heap cleanup, it moves. If it just stack bits, it copies trivially. These exact same rules apply to functions. Passing a string moves it to the function's scope, meaning the caller loses it completely. Passing an integer copies it, so the caller gets to keep it. Standard assignment acting across function boundaries. Functions can give ownership back by returning values. The string moves in and ownership moves back out. But shuttling tuples back and forth just to let a function temporarily read a value gets incredibly tedious. We need a better way to handle this. To recap, ownership means you move, clone or copy. To fix that function tedium, we need a way to borrow data without moving it. And that means references. But for now, you understand the core engine behind Rust's zero cost memory safety. Thanks for watching this BareMetal deep dive. Next time we will tackle exactly how differences and borrowing work to make your code cleaner. If this clicked you, be sure to hit subscribe and support the channel. See you in the next chapter.